Okay, so it should be recording now. Yeah, so who else has questions? So if you do have questions that you don't want recorded, you can probably send them to me in a private chat, or you can send them to me on the LMS. If you have questions before the sessions, you can always send me a question that you want answered, and then I'll try and answer it, and you can remain anonymous. Some more questions?
Sir, this is not related to the subject, but then, sir, I just want to know, sir, if you can understand vernacular.
So I understand a bit of Visayan, because my wife's Visayan and her family all speak Visayan. Gamai is all I can say. I can say Gamai. I got to see Gareth. But beyond that, so if you can ask your questions in English, because I think my geological Visayan or Tagalog would, I probably would struggle to understand it.
Okay, sir, I see, I see.
Some more questions about the course, the content?
Sir, is it okay if you could give us just one example on how to solve the partition coefficient? Because I just want to know which element should go to the solid and which element should go to the liquid, and so on.
Okay, so yeah, good question. So to actually know which elements are compatible and incompatible, it really depends a lot on what minerals are there and the composition of the magma. So I don't expect you to know which ones are compatible and incompatible. I have to look these up usually if I want to know. I can go through an example of a question of the kind of question that you might have. If I can make a new page. I can write that. Okay. Yeah. Okay. So I cleared that. So see a partition coefficient. So D. D is equal to the concentration in the solid over the concentration in the liquid. Yep. Let's double check this while we're around. So I don't expect you to remember all of these equations. I just expect you to be able to use them and understand how they're used. So I am just going to check as I go around. Yes, so it is the solid over the liquid. So then if you have, so the example I gave in the lecture was nickel in olivine, but it can be any element. So off the top of my head, I don't actually know many partition coefficients, but let's just say we have a mineral that has a partition coefficient G equals 2. So what that means is if you had 2 ppm in your solid, you would then you could work out what the concentration would be in your liquid. So from this, let's just clear this up. 2 ppm in your, so you can rearrange this equation here. So if we know this, and we know this, and we want to know this, the liquid, so we know the concentration in the solid, we know the partition coefficient, and we want the liquid, then what we do is we rearrange. We can multiply both sides by Cl, so we get, let me draw, D Cl equals Ds. And then we can divide both sides by D, so we get just Cl. Then Cl equals, we divide both sides by D, we get Cs over D. So if we know D is equal to 2, Cs is also equal to 2, you end up with 2 divided by 2, so the concentration of the liquid would be 1. And if this is ppm, then that's your units for your answer, would also be ppm. Yes? Do you understand how this would work? Would you like another example, or? Okay, so the way, let's see, I make a new page. If I clear everything, there we go. So just to remind you, partition coefficient is equal to the concentration in the solid over concentration in the liquid. And so the way we usually calculate these is we do an experiment. We put, say, an olivine crystal or a plagioclase crystal. We put it in a melt where we know this concentration, and then we measure the concentration in here, in the crystal, in the solid. So if we know these two, so say we have a melt with 1,000 ppm, so Cl equals 1,000 ppm, and we measure the Cs. So the concentration, let's call this a plagioclase, and let's say it's something like lanthanum. Doesn't matter what the element is, or chrome or something. And let's say we have a concentration of only 0.5 ppm. This is both ppm. Always remember to include units. If you don't include units in an exam or a quiz, you'll lose marks. So if we know the concentration in liquid, the concentration in solid, we can calculate the partition coefficient. So in this case, it would be 0.5 divided by 1,000, which should give us, this is where I get my calculator out, 0.0005. In this case, D is equal to 0.0005. And I apologize for the slightly wonky writing. It's not so easy to write on them. And so these are the kind of calculations that people do when they run experiments to work out the partition coefficient. But then you use them because when you have your minerals, your crystals, you'll often want to know what the composition of the melt was that they crystallized from. And so then you can measure CS and D and you get Cl. Or you might have worked out Cl from some other mineral and you want to work out what CS would be, what your concentration would be in a separate mineral. So yeah, you understand how this works, or another example?
It's okay, sir.
So other questions? More questions? More questions?
Sir, what's the difference between partition coefficient and the bulk partition coefficient?
Yeah. Good question. So they're the same thing, more or less. But when you just talk about a partition coefficient in general, you're usually referring to one for a single mineral. So for olivine or for plagioclase, for example. Whereas the bulk partition coefficient is for a whole rock. So usually you won't just have one mineral, especially not when it's partial melting. You'll usually have a lot of different minerals. And so what's important is the average partition coefficient of all those minerals. So that's all that's meant by the bulk one, is you have to average over your olivine, your plagioclase, your pyroxene, or whatever minerals are actually in the rock. Does that help? More questions? Any more questions?
Sir, subduction zones.
Sorry, can you repeat that? Quite hear what you said.
Possible that hotspot develop zones.
Yes, it's possible. There's hotspots. So they're caused by hot plumes, and the plumes come from either the boundary between the upper and the lower mantle, or between the core and the mantle. So these plumes start rising, and they don't know what's at the surface, so they can start rising anywhere. We don't really understand what causes them to start rising. So it's possible that you get a mantle plume that interacts with the subduction zone. It would then heat up all the material in the subduction zone, so you might expect a bit more melting. I don't think there's anywhere on Earth presently where you have a hotspot and a subduction zone interacting. Possibly around Yellowstone, although that's quite far from the subduction zone, but there is there's probably a mantle plume under Yellowstone. And then you have the subduction down the western coast of the US. So it's possible, but I don't think it actually currently is happening.
Okay, sir. Okay.
So keep the questions coming. I mean, you've had good questions so far. Don't be shy if you want to ask questions.
Sir, are we also going to have a virtual meet during our laboratory session?
Yes. So half the sections I'll be taking, and the other half Adrian will be taking. So I need to coordinate a bit better with Adrian over how he's done his. I'm not sure if he can actually set up the meetings properly in LMS. So for next Monday, if you're scheduled for the one Monday morning, then join whichever section you're in. You can join. I'll introduce the lab there. So the way it's going to work is I will introduce the lab. I'll give about 10-15 minutes talk on what you're supposed to do, show you how it's supposed to work, and then you'll have the rest of the time to work on it in small groups or on your own. You can do it whenever you want, so you have all the questions, all the materials online, so you don't have to turn up at the times that are in your timetable. But I or Adrian will be around during those times so to help you through it. So if you want help with the lab, try to turn up in those times. And so for the sessions that are the sections that I'm not taking, LMN 1 and 2, or LMN 2 and DEF 2, your sessions are not currently in the LMS, but I'll sort that out. So yeah, so there'll be a meeting like this where you can join and ask questions and do it as a group.
Okay, sir. So,
Sir,
Yes, go ahead. Yes,
excuse
go
me,
ahead.
sir. About 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 sa melting, sir, the decompression melting, sir. Ba? So why is it not because of heating, sir? Why is it because of decompression, man, sir?
So good question. I mean, if you're bringing the hot mantle up, you can heat up the rocks around it. So heating does melt rocks, but there's just not many situations where that actually happens. So in the mid-ocean ridge, when you bring your hot mantle, it doesn't heat up at all as it rises. It stays the same temperature, doesn't lose any heat, it doesn't gain any heat. So it's just as it rises, the pressure lowers, and that's what causes the melting, not because you're heating up something else. It's staying the same temperature, it's keeping its heat, and the melting temperature is changing because the
Of
pressure
pressure.
is getting lower.
Okay, thank you, sir.
Sir, can you further explain the utilization of batch melting equation and how can we interpret the diagram or model of it?
Okay, so let's get the batch melting equation. Here we are. Okay, I'll just share the slides. Okay, so can you see the slides now? Be able to.
Yes, sir.
Yes, sir. Yes, sir.
Okay, so the batch melting, so it's your concentration in your liquid divided by the original concentration. So we can only know what the concentration in the melt will be if we know what was in the original solid, which makes sense because if you have a lot of nickel, for example, in your solid that you're melting, you're going to have a lot of nickel in your melt. You have no nickel in your solid, you're not going to get any in the melt. So then it's a function of the melt fraction and the partition coefficient. So the way we usually use this equation is to then just model. So if we melt 10% of a mantle peridotite, what would our concentration in the liquid be? And so usually the way we use it, we can draw these graphs, and so we can see how different elements behave. And so there's a couple of things that we use this to try and do. One thing is we want to know what C0 is, what the solid was. So if we want to know what the mantle source looks like, and we know the concentration in liquid, we know the partition coefficient, and we can guess what the melt fraction is, then we can try and work out what the original solid, the mantle, has. We can also do this. This is, so estimating F is a bit difficult. It's hard to know what it is, although we can use highly incompatible elements. If you have something with a very low partition coefficient, much less than 0, this term here becomes close to 0. So if D is exactly 0, then any number multiplied by 0 is 0. So this disappears and you just have 1 over F. This is really small. This is really small compared to F. So your equation becomes the concentration in the liquid over the original concentration is equal to 1 over F. So if you have really incompatible elements, you can then try and work out what F is using this equation. And yeah, so, and it's not, so we don't usually just plug numbers in. What we do is we try to plot these graphs to see how the different elements behave, and so we can understand the difference between incompatible element and a compatible element, and how they change with melt fraction. Does that help, or you want still have questions about that?
It's okay, sir. Thank you.
Other questions? More questions? If you have any more questions, you have another 15 minutes to ask them now. Nobody has any more questions?
Sir, one more thing, sir. I'm a little bit confused lang po with regards sa decompression melting. And the first sentence, it stated there that in normal crust, sir, heat is transferred or is transported by conduction. Therefore, um, heat transfer because it is being touched with another object or another thing, and it's the reason of transferring heat. Then on the second sentence, sir, it says there that whenever that the crust is thin, whenever that the crust is thin, there's no heat transfer at all. Diba? According to that statement, it's adiabatically, so there's no heat transfer at all. So is it possible, sir, that as the mantle passes through or across to that specific section, this would never be a transfer of heat? Or if it is possible, sir, what will explain that phenomenon, sir?
Okay, yeah, good question. I'm just trying to find it. Maybe I didn't write it quite correctly. Um, so, so conduction does happen, and in the crust, all heat transfer, or the majority of heat transfer, has to be through conduction because nothing's moving. So you can transfer heat through convection only if your material can move. So if you have a fluid like water and you heat your pot of water from the bottom, you get convection because the fluid, the water, can move. The crust can't, it's rigid, it doesn't move, so you can't have any convection. So that's why most transfer is by conduction. For the most heat is transferred via conduction in the crust. So the second sentence, the statement about the mantle is separate. So yes, the mantle you will lose heat through conduction, but it happens really slowly. So in the crust, it has to be conduction because there's nothing else. But if the mantle, as it rises up, if it rises up quickly enough, then it doesn't actually lose any heat. I mean, it does lose a little bit, but we can treat it as if it doesn't lose any heat at all. And so then you're not losing heat through conduction, so that's why it stays hot. So there would be a little bit of conduction happening, but it's too slow to make any difference to the temperature. And so that's just in the parcel of mantle as it rises up, as it's upwelling. And then when it stops, if it gets stuck underneath the crust, then it will lose heat through conduction to the crust. But again, this is happening slowly. So it has to be still and not rising up for it for a long time for it to start losing significant heat through conduction. Does that make it clearer?
Yes, sir. Yes, sir.
Some more questions? You still have a bit of time to get your questions in.
Sir, I think we have no more question na, sir.
If you have no more questions, yeah, feel free to leave. I'll make the recording available as soon as it's finished processing, which will be sometime tomorrow.
Sir,
Yes, sir.
Yes?
sir, can I ask a question, sir?
Yeah, sure.
Medyo political siya, sir. Bro.
You can
Does
ask your
diet
question.
does diorite really have some bad effects, sir?
There's what? Sorry?
Does diorite, sir, ba, has bad effects?
This is based on what's going on in Manila Bay.
Yes, sir.
So is it? I think it's dolerite, not diorite, if I remember correctly. Dolomite.
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 Yeah, yeah. So dolomite is a rock. It's limestone, except with a bit more magnesium than regular limestone. And on its own, it doesn't really have any major effect. But if you're dumping a whole lot of sediment into a particular area, that can have effects on the habitat because the sediment gets washed into the sea and can be suspended. So it changes the environment if you put a lot of sand where there wasn't sand before. You also, it depends where it's extracted from. Extracting it can, because if you dig it up out of the ground, you're destroying what was there before. So I don't know enough about Manila Bay or the kind of ecosystems that are there to know how much of an effect it actually has. When I first saw it, I thought they'd dredged sand from a beach somewhere in Cebu to move there, which would have had a big effect on the beach they'd taken the sand away from. But if they're just mining, it would just be a quarry, so it probably has less of an environmental impact than dredging sand. But it's not really my area of expertise. So yes, you can if you put a lot of sand somewhere where there wasn't sand before, that's going to change the environment. So it could have an effect.
Okay, sir.
Yeah. So any other questions? Last chance to ask any questions. Otherwise, I'll leave you and then I'll upload the recording tomorrow whenever they send me an email to tell me it's ready. And then I'll see some of you Monday morning for the labs and hopefully everyone Monday afternoon for the lecture. Is there no more questions? So,
Questions.
yeah. Okay, so see you on Monday then.
Thank you, sir.
Thank you, sir.